Hello everyone. In this video, I'm going to be covering everything that's been the key for exam 3. So just in case you really screwed up this exam, and it seems like a lot of people did, I'm going to go over everything that's on the exam and just kind of talk about some of the concepts, especially the facts section, and really just emphasize how much you actually should know and how much, really you should have been able to answer. So I think for nomenclature, everything is pretty straightforward. If you made mistakes, then just do more problems. Make sure you see what you did wrong. Um, it looked pretty straightforward. The only thing that I thought was kind of like maybe you missed it was this phenyl ring, and just realizing that this is the parent. Okay. But besides that, if you, I'm sure there's many examples on past exams where you saw a phenyl ring. Uh, so you shouldn't have missed that. But besides that, nomenclature was pretty easy. Now, for facts was decently difficult. It was pretty unique compared to like some of the um, older exam questions. So the first one is probably the easiest one. You should have been able to get it right away. And this has to do with bridgehead stability. And this is a concept that is typically asked on the second exam. So for bridgehead stability, all we're looking at is the placement of where the double bond is. Okay, so if the double bond is not in the bridgehead, then it's fine. It's a perfectly regular double bond. It's nothing special about it. But if it is in the bridgehead, and the bridgehead is a location where where we have it attached to one of the bicyclic parts. The bicyclic part is where I have, a backbone, and I have an extended ring that's coming out of it. Okay, and you have this kind of like three-dimensional, no longer very easily two-dimensional molecule, right? So I have this part, right? If I have a double bond in this part where I have it over here and I have it over here, that has the bridgehead location. And when it is in the bridgehead location, I need to make sure that my ring is at least, I believe, 8 carbons, okay? And for these, when we check how many carbons, so what we're going to do is we need to check if the ring that contains the double bond, right, is at least 8 carbons. So I can either check this ring right over here where my mouse is going, or I can either check the ring that goes up into here where my mouse is going. So you always have two options, right? Obviously, regardless of which one you choose, whether you go up into here or whether you go down into here, they're both the same because it's both the same structure. Okay, here it's different. So if I count, starting from here, 1, 2, 3, 4, 5, 6, 7. Okay, so it's 7. So that means it's unstable. So because it's not 8, it's not stable. And that's why it's U over here. For this one, obviously I'm not going to count, but it's one more carbon, right? So it goes from like a 3-membered extension to now it's a 4-membered extension, right? We added another carbon right here. So that's going to be 8 now in the biggest outside ring. And so this would be stable, even though it's in the bridgehead position. Okay, so that's that question. Rank the electrophiles in order of increasing electrophilic character. 1 equals least electrophilic, 3 equals most electrophilic. So this should have been easy, right? And this is the real problem with memorizing the reactions, right? Because when you memorize reactions, yes, you can maybe kill the reactions part, but when it comes to other sections of the exam, you may not as easily be able to figure it out, right? Because you're not used to having to understand how the reactions work. And if you understand how the reactions work, you understand the concepts. That's where the concepts are derived from. So really, you have an opportunity now for the final to actually understand some of the reactions. And there weren't that many to understand, and they weren't that complicated either. But there are certain things you could get from the reaction. So in the reactions, we dealt a lot with attacking electrophiles, right? And we have been doing since test 2. But there's a specific electrophile that we've been dealing with, and that's the carbonyl. And the carbonyl is electrophilic because it has double bond oxygen to a carbon, and I have a potential resonance structure, but at the same time, what drives the structure is that those electrons can move up to the oxygen. The oxygen is pulling on those electrons in the first place. And I have that dipole moment, right? And I have a negative and I have a positive charge. And so I have those partially positive charges when I'm not resonating, right? And so this becomes a a electrophilic site, a site that can be attacked and can receive a pair, or can receive a bond, and yeah, essentially can be attacked. Okay, so either it's electrophiles are always partially positive or completely positive, um, and they can be attacked. They're always attacked by nucleophile, right? They're in pairs. So electrophile, we're looking at partially positive or positive, and we're looking at things that can maybe make that better or worse, right? So either maybe steric effects or inductive effects usually are the two main ones. There's also resonance. Resonance effects can be too. So let's just look over here. So electrophilic character, we're looking at, the carbonyl obviously is electrophile, the carbonyl carbon. So looking at the alcohol, is this electrophile? No, it's more of a nucleophile. It has free lone pairs that can be used to form bonds with things if possible. It's not a good nucleophile because it's not even negative, right? But it is a nucleophile. It has lone pairs that can be used to form a bond if need be. So this is 1 automatically. And now comparing these two, maybe if you had to guess, you would look, oh, chlorines, and you might think, okay, 3. But the reason why this is 3 is because this site is already partially positive, okay? But now I have 2 chlorines, 2 halogens that are extremely electronegative, electron pulling inductively through the sigma bonds. And so it's going to make that partially positive center, that carbon, even more partially positive. Now they're going to take away and they're going to pull away even more electron density away from that carbon. And so that carbon is going to become even more receptive to being attacked because it's even more partially positive now. So that's a 3, and the other one is just the normal, basic nothing. It's a 2. Okay? So you really try to think about these things. And yes, maybe we won't have an opportunity to go over everything in class or through an example, but if you understand, then you should be able to apply to some degree. Okay? And let's look at the next one. Place a Y in the box if it can produce a terminal alkyne using NaNH2 150 degrees Celsius, right? So this is the reaction. It goes from either a vicinal or geminal halides, usually bromide, chloride, doesn't matter, either or, and it'll form a terminal alkyne, okay? But the tricky thing about this question, there's 2 aspects to it, okay? One is a tricky aspect, and that is kind of subtle. So yes, any vicinal or geminal, any location on the molecule will form a terminal triple bond. Okay, but we have to be careful about where they are, and the surrounding environment. And let's just look at what I'm talking about. So this one is, straight away. This is yes, right? These will form the nearest terminal triple bond, which is right here. I'll form a triple bond right here. And that's perfectly fine, okay? But this one, they're both at the end. It looks very similar. However, I have this methyl group that's right here, and if I try to, even if I try to form the first one, and you think to yourself, well, yeah, but it'll move over here, but it can't, right? And it's blocked over here because I have this methyl group, and I cannot have more than one carbon group bonded to a triple bond. So this is stuck over here, and I cannot add any extra electron density. I cannot move past having a double bond over here. So I'll have a double bond, and then there's nothing else I can do, right? I have to have a hydrogen here instead of this methyl group. I need 2 hydrogens on each car. I need 1 hydrogen over here, and I need 1 hydrogen over here, wherever it is that you're forming the first triple bond. Okay? Because essentially it's an E2 reaction that happens twice. Okay, it's a little bit more complicated when you have 2 bromines, but it's not. But essentially an E2 reaction that happens twice. So if I don't have enough hydrogens, then it can't happen. And another way to look at it, instead of the hydrogens, just imagine forming a triple bond here. I cannot have a triple bond that has, let me use the sketchy pad. What I mean, right? Triple bond only has 1 group on one side. I cannot have this. This is wrong. Like it's too many bonds. So this is not going to work. So this is no. this is yes, right? This is fine. I can go in this direction, right? I won't be able to move this direction really. Um, you might actually, but this is the nearest direction and that you can form it in. Um, and this would be yes. And this one's no because it's seemingly you might get confused from the, I guess, the way it's drawn maybe, but they are not geminal orbital, right? Meaning that they're at least one apart or on the same carbon. So this is on this carbon, then the next one should at least be on this carbon, right? But the next one is on, let's see, wait a second. So this last one is very similar to this one right here. So this is a chlorine over here, is a chlorine over here, but instead of having the hydrogen group that I need, so this carbon over here has 0 hydrogen groups. It has a one carbon group, one carbon group, one carbon group, and a chlorine. No hydrogens at all. And this one over here has a hydrogen over here and a hydrogen over here. It has 2 hydrogens, but I need a hydrogen over here so that I can kick off this chlorine because that's how the E2 reaction works. So I will not be able to form a triple bond with this setup over here. Okay, so this is not possible. So this is also a no. Okay, place the compounds in order of increasing oxidation state. Oxidation state, simple way of looking at it is increasing bonds to oxygen. So, and let's say you didn't know that. Let's say you forgot. But let's say you had a general, understanding of the oxidation reactions that we did. We did several of them. And there's certain ones that were stronger than others, and I emphasize that a lot in the videos, right? Some of them were stronger than others. Like, for example, PCC is going to oxidize an alcohol only to a carbonyl if it's on a primary alcohol. But if I have a if I have like a Jones reagent, for example, and it's on a primary alcohol, it won't stop at a carbonyl. It'll stop at a carboxylic acid, right? So that's more oxidative. So if carboxylic acid to you, if you just told yourself carboxylic acid is more oxidative, then you should be looking for that, and that should kind of, imply that the more bonding to oxygen, essentially, right? So moving from alcohol to carbonyl is an oxidation, and moving from, aldehyde to carboxylic acid is an increased oxidation of that carbon, right? So this is not oxidized. It's only one bond to oxygen, so this is the lowest. This is 2 bonds to oxygen. And over here, this carbon has 3 bonds to oxygen. So this is high. It's very simple, right? So carboxylic acid is the most for most cases, and if you're even more than that, CO2 is the highest level of oxidation because it's 4 bonds to oxygen. Okay, and that's the most bonds a carbon can make. So CO2 is the highest oxidized thing. All right. Now, this last problem was a horrible problem. And I'm sure it got many people that knew how to do this problem. And it's on every test. And that was the problem. This type of problem was on every single exam. But the way it was on every single exam, it was very different, right? So I'm just going to pull up really quickly to show the alternate. Come on, what the hell? Let's see. So test 3. I'm just going to pull up any exam, okay? Let's scroll down. All right. It says, place a Y in the box below any halide that will produce a useful Grignard reagent. It looks exactly the same. Any halide that will produce a useful Grignard reagent. Let's look at what she has. Place a Y in the box below any compound that will react with a Grignard reagent. So it's a really small difference, but it makes a big difference. And so the first thing should have been that none of these molecules have a halogen on it, so none of them can become the Grignard, right? I need a halogen to become a Grignard, right? So none of them have that, so that should have said something. But even still, I know sometimes we get into repetitive kind of movements or thinkings that we use to do things easily, whatever. But we really didn't. That should have been the first thing that you saw. But the bad thing about this is that everything that normally you would have put no on would be yes, and everything that you put yes would be no. So Most people cut completely all the points off for this, unless they made a mistake, which would have been nice. But it's the complete opposite. So it said any compound that will react to the Grignard reagent. So before, we're looking at any compound that has nothing acidic and nothing electrophilic, right? And then we put a no for anything that does have that. For this one, we're putting a yes for anything um, we're putting a no for the things that have only nucleophilic parts and have and yes for things that have the electrophilic parts. So everything that you would normally put no over here that could be attacked by the Grignard, you put no over here. But over here we want things that can be attacked by the Grignard. So now N double bond, yes. C triple bond, this hydrogen over here, yes. Regular double bond, no. This NO2 group, yes. This acidic hydrogen, yes. And nothing over here, so no. And so that was the big crux of that problem. Hopefully the reactions are pretty straightforward and you can see. I'm not gonna waste my time doing this. Everyone should. I went through them already. They're decently very straightforward. Okay. Now the mechanism is actually very atypical. I haven't seen something like this really before, and I actually probably would have gotten points off of this, and it's fine. Sometimes you take points off. I've never made 100 on any of my exams. You know, hope to. I hope to, but didn't get to. There's always gonna be little things that you're not ready for, or you haven't seen, or she's trying to trick you up, or maybe you test anxiety, whatever. So that would have been nice if that was the part that you got points off for, but unfortunately, I think it threw off a lot of people. Um, but let's just see. Okay, so sadly, it wasn't that complicated of a mechanism. It would have been actually. I think people would have done better on it if it was more complicated and how it normally is that you see it. So the first step is, of course, a protonation of the H2O group. Okay, and you have a strong acid here, so this is going to get protonated because this pKa value is far lower than this pKa value, and so this is more basic, this is more acidic, and that's going to be a very good leaving group. Now, the part that I probably would have forgotten, but I would have been suspicious of it. I would have not, been comfortable doing this, is using a halide shift to kick off the leaving group. And the reason why we have to do this here is because I have a leaving group, right? I have this weak leaving group that's not normally a leaving group, and it's just like SN1 and E1, right? The leaving group will only leave if it's on a secondary or tertiary carbon, not on primary, because it's not stable to have a carbocation on a primary carbon. So I have this leaving group that would form a primary carbocation if it did leave. So I have to always, when this happens, to kick off that leaving group, I have to get something to make it go, right? And this is kind of like SN2 a bit, right? SN2 a bit works on primary and it forces it to leave, right? I attack, or is essentially attack almost, and I kind of make it leave. And so we're using this hydrogen in a weird way, and we're shifting it. It's something that we would have done already in the next step. So maybe you did it in the next step. You just made these two separate steps instead of one. But it has to be one because the only way for this to leave and properly, right? It won't leave in good amounts if this was not here. So the only way to make this leave is to make this shift over here and then kick it off. Okay, and then you will form the carbocation over here, tertiary carbocation, and at this point, we're going to have the ring, a ring formation, and we're going to use the double bond to attack the carbocation, and we'll form this 6-member ring that's joined up with this other 6-member ring. And then now we just have 2 sites to form the new double bond. And this is another part that I might have done differently. I did it differently in class. Maybe my thinking was not right. But it is very easy at this point. The only reason I would have done it differently is because I thought it was like way too easy just for it to be the major and minor products of this first E1 reaction. And so it's just you deprotonate these 2 individual hydrogens and you form the 2 products like that. What I would have done is the first product I would have done normally, and then I would have done like a halide shift and then I would form a double bond from a carbocation over here. And the reason I would have done that was because that way I have two separate like paths of the molecule that forms, and in both cases they're both the major product. But just ignore what I'm saying because it's not what she did. Okay. So this is perfectly fine, simple enough. Okay. So the only thing is just this first part. And if you got this wrong, the high drive shift would have been a whole 4 points. So that really sucks. Um, and this really sucked too, because she was not that many steps. So like if you screw up in one part, then you lose a lot of points for something really small. And then the last thing is synthesis, and synthesis was decently easy, I thought. So first step, we have to always, whenever you see a carbonyl, right, we cannot form a carbonyl through at the end of a nucleophilic step, right? So we always attack carbonyls when we form alcohols, but I can never like attack something and then magically I have a carbonyl. So that means that I have to do a reaction to revert it back to an alcohol. I love alcohols in synthesis. We all should love alcohols in synthesis because that means I can do a Grignard step or some other type of thing and just do then H2 plus and then I'll get the alcohol. The alcohol lets us cut things. It's very nice. So I have PCC just so I can go back to an alcohol. Okay, and I use PCC and not Jones because I have this aldehyde and not the carboxylic acid. So I form primary alcohol, and in my opinion, you might have done something differently, but this is the best thing to do, is to use the epoxide. And how do you know when to use the epoxide? Well, you know when to use it, specifically when you have the OH on a primary, it's a primary alcohol. So the epoxide is always going to look like this. That's the way you're going to usually draw it, and you're going to have something come and attack it. Okay, so the epoxide is 2 carbons, which is this carbon right here. Let me just take a picture of it so that I can kind of make little notes on this. Right? So I have this. This is a primary alcohol. The epoxide is 1, 2 carbons long, and this is 1, 2 carbons long. And so that means this was cut right here. Okay? And so I'm adding this whole group. Okay, I'm adding this whole group right here to this guy. Okay? And so that means the Grignard part, the MGBR part, has to be coming off of this carbon right here, this guy. Okay? Does everybody see that? I hope everyone sees that. And so this is going to come and attack here, and this is going to, regardless, both sides are the same, but there's always attacks from the least substituted side. Here it's the same, and this is going to come and attack right here, and this is going to pop off. Okay, and it's going to pop off, and that's how it becomes a primary alcohol. And so that's good. I'm having a big smiley face. Okay, so from here, the epoxide, you can just use MCVA, go back to an alkene, and I think you're allowed to go back to an alkene. Yes, sir, I am. And then from here, it's pretty simple. And I'm gonna go back to her exam. And so from here, it's pretty simple. That's why epoxide is the best thing to do. And if you see a primary alcohol, it's like a good time to use an epoxide. It shaves off 2 carbons and it makes things a little bit easier. Otherwise, dealing with a primary alcohol is a bit of a pain in the ass. So now I have the Grignard Mg and ether, and that's add the Mg part. Now go back to a Br, and then I don't want to use Br2 and light here because I'm not going to really get great yield because I can have I have 2 locations that I can be substituting that bromine on, either here or over here, because it's not a symmetric. It's symmetric, but I have different environments. And so obviously it's a bit too early also as well to use Br2 and light. So to those of you that did, we should use PBr3, and this is for secondary and tertiary. It's for secondary and tertiary, I believe. I always mess it up. But secondary and tertiary. And so we'll go back to an alcohol, and then now that I have an alcohol, I can do cutting again because alcohols mean that I can go back to a carbonyl. And so I have a carbonyl on this side, and I have this on this side. And so you have that, right? and the rest should be easy peasy, right? The only part was this, I guess the first part. The beginning is always the most difficult. The rest is kind of just, repetition. Okay, so hopefully that makes sense to everyone. All right, if you have any questions, please feel free to email me. Obviously, like my YouTube account is tied to a Gmail account, so email me if you have questions. I'm open to it, and I'm happy to answer. All right, best of luck on your final and studying.